What's up, everybody? It is great to see all y'all hooligans. It's, it's just great to be here doing some calculus, man. We're doing some more FRQ review, the 2021 AP exam, question number 4. And it's looking like we got a graph of F. We're going to be answering some limits, got an integral, looking like an average rate of change. So all around the place. This should be super informative, and I'm hoping really helpful for you guys because I'm making these videos so that you guys can succeed on the AP exam. That's the point. So I really hope you guys are growing in your knowledge and hopefully also love of calculus. But let's take a look at this question together. So question 4 gives us a graph of f, and then it says let f be a continuous function defined on the closed interval x is between -4 and 6. The graph of f, consisting of 4 line segments, is shown above. Let g be the function defined by g of x equals the integral from 0 to x of f of t dt. Okay, so that's what we got. We got this function f. G is the integral of f from 0 to x. Okay, part A. Let's see what it says. Part A says, on what open intervals is the graph of g concave up? Now, g of x is equal to the integral from 0 to x of f of t dt. Now, we know that concavity relates to the second derivative of a function. So if we're looking to see when g is concave up, that is where our second derivative of g is greater than 0. So let's find the second derivative, right? So our first derivative of g, we can use the second fundamental theorem of calculus, which says if I'm taking the derivative of the integral from some constant to x of f of t dt, this derivative is just f of x. So now when I take my second derivative, I just get f prime of x. So when I say I'm looking for where g is concave up, really what I'm saying is I'm looking for where f prime is positive, or where f is increasing, right? Where a slope of the tangent line is positive. So we look at our graph from -4 to -2. F is definitely increasing. F prime is positive. And then from 2 to 6, F is also increasing. So therefore, F prime is positive, G prime is positive, and our function G is concave up over these intervals, right? So that's part A. Relatively easy, honestly. Off to a super solid, quick start. I'm liking it. I'm liking the way we're going right now. Gotta make sure I'm centered here. I don't want to make sure. Oh, shoot. I can't see. Hopefully that's centered. Who knows? I want to make sure you guys can see the incredible work that I'm putting on paper, you know? Let's look at part B together. So part B says let P be the function defined by P of x equals G of x times f of x. So it's these two functions multiplied together. And it asks us to find P prime of 3. Now, we're trying to find the derivative of this function. To take the derivative of this function, I'm going to need to use product rule, right? Because I have two functions multiplied together. So I'm going to do my first term, just g of x, times the derivative of my second term, which is f prime of x, plus the derivative of the first term. What's the derivative of g to the x? Well, it's actually f of x, right? Times f of x. So now I'm going to, plug in 3. I'll get p prime of 3 equals g of 3 times f prime of 3 plus f of 3 squared, right? Because it's just f of x times f of x. So let's think about it. I can solve for f prime of 3 and f of 3 really easily, right? At 3, looking at my graph of f of x is equal to negative 3, right? So this will be negative 3. Now, f prime of 3 is the slope of that line at x is equal to 3. We check it, rise over run, it's equal to 1. So f prime of 3 is equal to 1. We're almost there. We just need to find g of 3. Now, g of 3 is going to be a little bit more difficult, right? Because g of 3 is equal to the integral from 0 to 3 of f of x dx. And we don't have a way of necessarily solving this with calculus. It's not like a u sub, obviously, nothing like that. But what we do have is a graph of f. And I know that I can find a definite integral of a function that is graphed by finding the area under the curve. If the area under the curve is above the x-axis, will contribute positively towards the integral. If it's below the x-axis, it will contribute negatively. So you guys have the graph over here on your left, but I'm going to do my best to draw a little picture for a function just to show what's going on. So it hits the x-axis right there, kind of goes straight down. That wasn't great. But then it just kind of keeps going straight down, and then it goes off to the side like this. So this is x equals 1, it's x equals 0, this is x equals 2, then x equals 3 is somewhere around there, okay? So to find this integral, right, that'll just be the area under the curve. Well, this first triangle has a height of 4 and a base of 1. So it has an area of 2. It is above the x-axis, so it will contribute positively. Now, I'm going to kind of split this second shape, which is kind of weird, into two separate shapes. So I'll have a triangle and a trapezoid. This first triangle has a base of 1 and a height of 4, if we look at the graph. So its area will be negative 2, but it is below the x-axis, so it will contribute negatively. Now we have this trapezoid. This trapezoid, its first base is 4, second base is 3, its height is 1. So the area of this trapezoid would be 4 plus 3 divided by 2, which is 7 over 2 times 1, or 7 halves. But once again, because it's below the x-axis, it will contribute negatively. So the answer to that is negative 7 halves. So now I can just go ahead and calculate this, right? This is equal to, those will cancel out, negative 7 halves. So now I plug that in into g of 3 up here, and I will hopefully get my final answer. P prime of 3 equals negative 7 over 2 times 1 plus negative 3 squared, which equals negative 7 over 2 plus 9, which if I were to simplify it into one fraction, gets me 11 over 2 as my final answer for part B. So that was a tough one, a little bit of a challenging one. Figuring out this g of 3 based on the area under the curve, a little bit tough. Got to split it up into some shapes. But that process of finding an integral based on area under the curve, I feel like is relatively commonplace. That's something that we should be picking up at this point going into an AP exam. We want to kind of have that locked down. So hopefully this part was very doable for most of us. But let's move on to part C. So part C is all about a limit. And I have said this before, but I am a big fan of limits. I don't know why, but limits in calculus I just find really fascinating. This question says, find the limit as x approaches 2 of g of x divided by x squared minus 2x. Okay, so we're doing a limit. First step, if we're ever solving a limit, direct substitution. Plug it in, see what we get. So if I plug it in, I get g of 2 divided by 2 squared minus 2 times 2. Now, obviously, our denominator is just going to be equal to 0, but our numerator, we're not quite sure about, right? Now, we just solved for g of 3 in part B. Now we're trying to solve for g of 2. If I look at this little graph that I got, right, our function starts at 0, 4, and it drops down until 2, right? And if I find the area under these curves, these triangles actually have equal area. Both of these triangles have area of 2, but one of them is above the x-axis, one is below the x-axis. So the integral from 0 to 2 of f of x dx will be 2 minus 2, or just 0. So this whole limit, when I direct substitute, is just 0 divided by 0. And this is an indeterminate form. When I get an indeterminate form, what am I going to use? L'Hopital. And that tells me that this limit's value is going to be equal to the value of the limit as x approaches 2 of the derivative of g of x. Well, we've talked about earlier, the derivative of g of x is f of x divided by the derivative of the denominator, which is 2x minus 2. When I plug in x of 2 now, doing that direct substitution step, I get f of 2 over 2 times 2 minus 2. I look at the graph to find f of 2. It's equal to negative 4. 2 times 2 is 4, minus 2 is just 2. Negative 4 divided by 2 is negative 2. And that gives me my final answer to C, which I think is a solid one. I think this step specifically, finding the integral from 0 to 2, giving us g of 2, if we were really paying attention in part B, we would remember, wait, okay, these triangles were the same. One was positive, one was negative. I mean, we even look back. We saw that 2 minus 2 canceled out, and we were just left with the integral from 2 to 3, right? So doing this step quickly, because we remember what we did in part B, makes this question go by really, really quickly, where if you need to more take your time on this step, it could hold you up, be a bottleneck for the rest of this question. But I love limits. I thought this was a great question. But yeah, final answer, negative 2. And we will move on to our final part to this question, part D. I always expect part D's to be the hardest one. I don't know if that's actually true or not. It always feels like it, though. It feels like A is kind of separate, and then B and C kind of joined together, and then D is always just hard, Let's check this out. It says find the average rate of change of G on the interval from negative 4 to 2. It says, does the mean value theorem guarantee a value C for which G prime of C is equal to the average rate of change? Justify your answer. Okay, so let's start with the first step. Find the average rate of change of G on the interval from negative 4 to 2. Now we know the average rate of change for a function is equal to f of b minus f of a divided by b minus a, right? But we're dealing with the function g, right? So if I were to put this in terms of g, it would be g of our right endpoint, which is 2, minus g of our left endpoint, which is negative 4, divided by 2 minus negative 4. Now, we already solved for g of 2, actually, in part C. So everything's kind of coming together. G of 2 is equal to 0. G of negative 4 we still need to solve for. But 2 minus negative 4, it's double negative. We'll get 2 plus 4, which is equal to 6. So all we need to do now is solve for G of negative 4. And that will tell me the average rate of change. Now, G of negative 4 is equal to the integral from 0 to negative 4 of f of x dx. And I know that definite integrals of this function, I can figure it out using the area under the curve. Now we got to be careful, right? These bounds are mixed. We got the bigger value first, smaller value second. So I'm going to flip these two bounds. Say that negative g of negative 4 equals the integral from negative 4 to 0 of f of x dx. And now I can solve this integral geometrically. It will just be the negative of g of negative 4. So let's do it. I will draw out the sketch for probably the final time. Let's take a look. So we start at 0, 4. Then we go up to negative 2, negative 6. And then we go all the way down to negative 4, 0. So these are our three main points. And I want to find the area under the curve, right? From negative 4 all the way to 0. So I would split this up into two different shapes, a trapezoid and a triangle. This first triangle has a base of 2, a height of 4, so its area is equal to 4, which is 4 times 2 divided by 2. Oh, I'm so sorry. A height of 6, not from 0 to, we're not going up to 4, we're going up to 6. So it'd be 2 times 6 divided by 2, which is 6. Now this trapezoid, it has a height of 2 and bases of 4 and 6. We know the area of a trapezoid is the average of the bases times the height. The average of the bases is 4. Or 5, goodness. Multiply that by 2, and I get 10. So I get negative g of negative 4 is equal to 16. So g of negative 4 is equal to negative 16, right? So I could plug this in. I actually get minus g of negative 4 right there. So I'd just plug in 16. 0 minus 16, which is negative 16 over 6, which I could simplify to negative 8/3. So that is my average rate of change. Now that is my first step of this problem, but we have a second part, right? It says, does the mean value theorem guarantee a value for which g prime of c is equal to this average rate of change? And here's when mean value theorem works. Mean value theorem is true. I'll say mean value theorem is true for any function. In this case, it is g on an interval when g is continuous and differentiable. And that means that our function exists at every point, it's continuous, but the derivative of the function also exists at every point. So meaning our derivative is continuous, right? So what's our derivative of g? Well, our derivative is f. And because f is continuous, that means our derivative is continuous, and therefore our function is differentiable across all these values, right? So, therefore, mean value theorem can guarantee a value c, such that this holds. So remember, for mean value theorem, right, all that needs to happen is for our function to be differentiable, which also means it's continuous, over this interval. So therefore, there must be a point where our instantaneous rate of change equals our average rate of change, which is -8/3. So that was a tricky part. Part D was a little tough. Finding this integral -16, tricky, right? Setting this up, tricky. Using mean value theorem, trick. I mean, this was a hard question, right? And only worth 2 points. I thought this was a lot of work for only 2 points, but I stand corrected, I guess, right? But a lot of great concepts that we went over with this question. Number 4, I hope that you guys really gained something out of it, whether it was an understanding of mean value theorem, whether it was these definite integrals relating to area, who knows, L'Hopital, whatever it was. I hope that you guys have just gotten better at calculus watching this video. But thank you so much for being here with me, and I cannot wait to see you in the next video.